Hey everyone, this is just a review of what we're going to be covering on the test, what you need to remember, what you need to study. Um, so as you're kind of going through this, if you have the review packet that I've put out attached to this on Classroom, you can kind of work through the problems you just go through. There are no problems in this review um, video to work on, just the examples that I'm going to show you just to remind you how to do it. They're the same examples we had during the unit. Um, just so I can remind you what we're doing, what we're looking at, how we're going to do the problems. So if you want to work through the problems on the review packet, do that as you kind of go through so you can just make sure you understand what you have to do. If you have any questions, as always, send me an email so I can kind of look and see, and I'll try to send you a result with what's going on, whether it's a quick another video I send you or just an email back reminding you how to do some stuff to get through that. So let's get going. So remember we started off with circles. It's basically a circle consists of all the points in a plane that are the same distance from a given point in the center. So I think we all know what a circle is. The radius is that segment with endpoints that are on the center and the outside edge of a circle. Pretty sure we all know what the radius was. The chord is the new thing. In our diagram, a chord is these ABs, or AE. It's a segment or line segment that goes from one edge of the circle to another. Doesn't have to go through the middle. If it does go through the middle, then that's what we're talking about when we're talking about the diameter. Just remember, a diameter is a chord. But the chords are just points where the endpoints are on parts of the circle, on sections of the circle. So it's just a matter of what part is it and that it's called a chord. So we talked about the circumference again. Remember, circumference is 2 pi r. It's 2 times the radius times pi. Again, remember we talked about the two different ways to ask for results. Like in our example, we're looking for the nearest hundredth. So we're rounding to the nearest hundredth when we're doing our example here. You may have some problems where you're asked to find the exact measurement. So remember, when we're finding the exact measurement of a circumference or an area of a circle, or in another example, an area of a sector, we're looking for that answer to be left in terms of pi. Because we all know that pi is a never-ending decimal. We can never actually get the exact value for what pi is. We're always estimating it. So if we're looking for the exact value of the area of a circle, or in this instance, the circumference of a circle, you leave your answer in terms of pi. Similarly, if there's a problem on the review packet or on the test that's, again, looking for the exact measurement of, say, area of a circle, and you know the radius as a radical, 3 square roots of 2, 2 square roots of 3, the square root of 5, you need to list if it's the exact answer they're looking for. You actually need to leave your answer in a radical form, whether it's a simplified radical or just have the square root in there. Because like an example of the square root of 2, the square root of 2 is an irrational number. It goes on forever. We don't know what the actual value of the square root of 2, if it actually ends or not. So just remember, exact values, leave it in terms of pi, or in a radical form, rounding to the nearest hundredth, then you're able to do, the square root of 2 is 1.414. Pi is 3.14. You're able to make those assumptions and those estimates to calculate the values. So in our example here, we're looking for the circumference of the circle rounded to the nearest hundredth. So I know my circumference is just going to be 2 times my radius is 13 times pi. Again, like we always say, if you're going to use an estimate of pi, use 3.14. It's the easiest one to use. Everybody knows it. So all you're doing to find the circumference here is just 2 times 13 times 3.14. And you'll find out that our circumference for this circle is 81.64 centimeters. If you were asked to round to the nearest tenth, then it's 81.6. If we wanted exact value, it's 26 pi. So remember that as you go through. Okay. Along with circles, we talked about inscribed and circumscribed polygons. Remember, these come up a little bit later on in the tangent unit, especially the circumscribed polygons, because we know now what we mean when we say the sides are tangent to the circle. But like I said, the circumscribed polygon is a polygon where each side is tangent to the circle. Basically, a circle is drawn inside a shape, and the circle touches all the edges of that shape. The next one, the inscribed polygon, now that's a shape where the circle is drawn around the shape. The circle is touching all the vertices of the polygon. So if it's a quadrilateral like we see here, it's going to have 4 vertices touching the circle. If it's a pentagon, the circle is going to touch all 5 vertices. So the shape is completely drawn inside the circle, touching the circle. And again, we'll be able to use some information from this to do some other stuff, which you kind of learn a little bit later on in the unit. What we did remember for shapes like this, if we have a triangle that cuts through the diameter of our circle that's inscribed, then that triangle forms a right triangle. Again, we'll need this a little bit later on when we do some other stuff. So just remember that when we're looking at when you're looking at an example like we have here, asking for the diameter of that circle, it has an inscribed triangle that we see the hypotenuse of our right triangle goes through the diameter, which is why we can say it's a right triangle, which then helps us figure out our diameter to then find the circumference, because now we know right triangles, excuse me, Pythagorean theorem helps us identify the diameters. So we look at our problem here. We have a side of 6 and a side of 8. We may be able to recognize that as a 3, 4, 5 triangle. If we do, that tells me that my hypotenuse is going to be the 5 times 2 side. So my diameter then is 10. Again, if you don't recognize it, that's okay. Just use the Pythagorean theorem. 8 squared plus 6 squared is going to equal c squared, or diameter squared. When you do that math out, it comes out to 10 as well. So now I know our diameter is 10. They want the exact circumference of my circle. So we remember that circumference equals 2 pi r. Excuse me. If I rewrite this, it equals 2 times r times pi. So when I look at that, I remember 2 times the radius, that's just the diameter. A radius is half the diameter. So my diameter for the circle is 10. So my exact answer is just 10 pi for the exact circumference of that circle. They're looking for exact, so leave it as 10 pi. Don't multiply it out. You will, on like the MCAS test, you will get it wrong. In my test, I'm not going to give you full credit because you didn't give me the exact circumference. Okay, moving on again. As part of the circumference of the circles and stuff we learned about measuring arcs and angles. Central angle, that is the angle where the vertex of the angle is at the center of the circle, and the 2 sides go out as radii from the center. We know that they go out and create what they call an arc. So my radii go out from the central angle, they touch the edge of the circle, that creates an arc between those 2 endpoints. In my diagram here, we have point C and point F. That's arc CF. So that's how it creates an arc. Remember, there are 2 types of arcs. There's a minor arc, which is the shortest arc of connecting 2 endpoints on a circle. So if we look at arc C, I'm going to kind of change my thing here. I'm going to erase what's there and kind of do stuff in highlighter. So we're going to talk about arc CF. So the minor arc for CF, it's the shortest distance connecting 2 points. That will be from C, that's not highlighted, but I'll draw it in yellow. That will be C to F. That is the minor arc. I'll circle minor arc in yellow so you can remember. So that tells me that is the shortest. Minor arc is always 2 letters. So it's well, not always. I can't say always. Let me rephrase that. More often than not, the shortest arc, the minor arc, is going to be identified as 2 letters. So in our example here, we have CF. If you saw an arc named CFG, that's telling you to go from C through that F, from C to G through the F point. So we kind of switch over here now to the major arc. I'm still using CF. We're going to call that major point, major arc goes from CF the long way around basically. Think of it taking the longest route around our circle to get to that point F. So you can kind of always think of it, if you travel and understand travel, you're trying to fly to London, England. The short arc is going from Boston to London over the Atlantic Ocean. The major arc would be from going from Boston to London by way of the Pacific Ocean and all the way across Asia. So the major arc, I'll circle it in green to remind you, that's going to be identified by a 3rd letter. So in our example here, we would call it arc CHF. That tells us to go to point F from point C through point H. So it's telling you which way around the circle to go. The minor arc is always just going to be CF, and that's what it's always going to be. So typically, you're going to see minor arcs listed as 2 letters. Major arc will be listed as 3 letters. They're both going to kind of have the cap over it, whether it's a hooped cap or the pointy cap. That's what you're going to see. Remember that the semicircle, it's not really either a minor or a major arc, it's the diameter. So the semicircle is an arc that has its endpoints on a diameter. We don't actually have one drawn in here, but if I drew a red line in here, we call that A and B. My semicircle now is arc AB. That tells me that AB is the diameter, so then I'm able to kind of figure out what information from that. So just remember that as we're talking about these things. You'll be told if something's a semicircle more often than not on a question. So we had the properties of the central angles, if we remember that, central angles and arcs. The sum of all the central angles in a circle are going to add to 360 because it's how many degrees there are in a circle. The measure of the minor arcs, measurement-wise in degrees, is always going to be less than 180, and it's equal to the measurement of that central angle. The measurement of the major arc is always going to be 360 minus whatever the minor arc was for that 2 points. So you can always figure that out. Semicircle is always 180 degrees because semicircle, it's halfway around the circle. Minor arcs are congruent if and only if the corresponding central angles are congruent. So I have 2 central angles that are 50 degrees, then I know those 2 arcs for those 2 angles are congruent. And then 2 adjacent arcs formed by central angles, we can add the 2 angles together to figure out what that the bigger angle is now, just kind of like when we did adjacent angles back when we were working with angles. Okay, so I have our example here. They're looking for the measurement of arc AB and the measurement of arc ACB. So ACB tells me major arc. They want to go the long way around. AB is the short arc, which I'm just looking at that. That's my central angle measure. So the measure of arc AB is just 42 degrees. Fairly easy, fairly self-explanatory. On the circles, as they draw the circles out, they're always going to have to give you probably at least 2 angle measures in a circle to be able to figure out all the other arcs from that circle, as you kind of looking at problems on the test and on the review packet. They also wanted the measurement of arc ACB. So remember, ACB is just the major arc, so that is the measurement is going to equal 360 minus the minor arc. So we have 360. My minor arc for AB is 42. Not equals, that's going to be minus. minus 42 degrees. So that tells me that the major arc there then is 318 degrees. Remember, when we talk about that's going to be something you're going to need to know when we start working with sectors and areas of sectors and even arc length as well, which I think is the next section of our review thing, to make sure we're able to calculate what the actual numbers are we're looking to calculate with the major and minor arcs. So again, I hope this makes sense and hope everybody remembers this. Moving on to arc length, like I said. So arc length is just basically figuring out what is the measurement, the distance between the two endpoints of the radiuses that form a central angle. It's calculated as part of their circumference. So think of it as a percentage of our circumference. Circumference of the circle is 2 pi r. We're looking for a percentage of that for the central angle. So the formula we're going to look at, our arc length they kind of use as a cursive L, is going to be the central angle divided by 360. That's basically telling us what piece of pi makes up the percentage of the circle, the percentage of the circumference. And then we're multiplying it by the circumference. So we're looking for central angle divided by 360 times 2 pi r. Fairly self-explanatory, fairly straightforward. As long as you kind of start looking at it, we're always going to have to give you enough information to calculate it. So again, we're going to look at arc AB. They want to know how long arc AB is. So we use our formula. We have 360, some number over 360. We want arc AB, so we're talking about the minor arc. We're talking about the short distance. 2 letters is the short distance. So my central angle is 135 degrees. We can divide that by 360. Then I'm going to multiply it by my circumference, 2 times 8 for my radius, times pi. Again, we look, nearest hundredth. They want us to round it. So we do the math out. 135 divided by 360 tells us the percentage of the circle. It's 0.375 if you want to see what it looks like. So that's 0.375. That's going to be times 16 pi. So now we just do it out. 0.375 times 16 times 3.14. We find out that this is 18.84 inches. So if you had calculated the full circumference of the circle, the 16 pi, whatever that worked out to be, that would be 16 pi times 3.14. That's 50.24 inches for the full circumference. So now I know that 37.5% of that is the 18.84 inches. If they told us and they wanted ACB now, they wanted the length of ACB, we're switching that up and we're doing 360 minus 135, which is 225. My mistake. 225 divided by 360. Again, though, it's still times 16 pi. So that would end up being, worked out perfectly. This is 0.625 times 16 pi, which now I know should be somewhere about 32 when I do this. $31.4. So that's the circumference of the major arc there. When we add them together, 31.4 plus 18.84 works out to be the full circumference of 50.24. So that's what you're going to be doing. You're looking to see, did they give me 2 letters for my arc? Did they give me 3 letters? What's my central angle? We'd even be able to figure out the arc for CB. You just have to do 180 minus 135 to figure out what that central angle is. You use the same formula. You may be given a question on the test to find all the measurements of all the arcs in the circle. Okay, so arcs and chords. We have all these chords drawn in, cuts across points of a circle. We know that we can have a central angle based on two endpoints on a circle. So basically every chord will correspond to a central angle by then connecting the endpoints cutting across the circle. So my chord RS there, I can draw in radiuses from O to R and O to S, created my central angle. Draw the chord across from R to S, now I have my chord. So the arcs and the chords are related. If minor arcs are congruent, then the chords that are corresponding to those minor arcs are congruent as well, and then vice versa. If the chords are congruent, the minor arcs are congruent. So if we end up getting a picture like that the chords are congruent, then I know right away that my arcs are congruent. So we can do some stuff, some math from that to help us find some values as we go forward in this unit, if we remember. We talked about bisecting arcs and chords. The diameter, if a diameter of a circle is perpendicular to a chord, in our example here, WZ is perpendicular to AB, then the diameter bisects the chord and the arc. So it cuts it into two equal parts. So from what we know then, side AX is congruent to XB, and arc AW is congruent to WB. You also have the point where two chords are congruent if they are equally distant from the center. So if I went in and said that OX is congruent to OY in the green, then I can say that RZ is congruent to ZF. You'll be given all that information on a problem. You just have to remember what you need to do with it. Remember, these were a lot of the algebra problems where you'd be given algebra measurements to figure out arc length or arc measurements and then chord length. I think we have an example. Nope, we didn't have an example. Sorry about that. So just kind of look through. There is a lot of problems in the review packet that kind of covers the arcs and chords, and calculating what X values are and how long chords and arcs are from that. Inscribed angles, we talked about that. This will help us kind of when we get into the inscribed polygons. An inscribed angle, again, is an angle that has the vertex on one side of a circle and the endpoints of the other, the chords from the form that angle have endpoints on the other side of the angle. So in our example, our picture, we have circle O. We have DEF is the inscribed angle, because vertex at E is on the edge of the circle with the other two endpoints on the opposite side of the circle. They don't always have to be on opposite sides of the circle. I could create this inscribed angle here, not drawn in well, but it's inscribed. I have a vertex, I have an endpoint, and I have an endpoint. So I know it's not drawn well, but it doesn't have to be all the way across the angle, all the way across the circle. What we remember from that, though, is that the inscribed angle's measurement is half of the measurement of the arc. So if they told us that arc DF was 120 degrees, I know that angle DEF is 60 degrees, because it's half of the arc. Conversely, if they told me that the angle was 50, then I know my arc was 100, because it's twice what the angle is. So that will help you as you kind of start piecing together some information and some problems with working through some stuff. So just remember, kind of try to remember this kind of relationship, that the angle is half of the arc measurement. Our example, we still have circle DEG. Again, they tell us that arc DF from D to F is 90 degrees. My angle is 1/2 of the arc length, DF, so 1/2 of 90 makes angle DEF 45 degrees. Does that make sense? Does everybody remember that? We need to, you'll be some problems on the test for that as well. Okay. The angles of the inscribed polygons. This is why we kind of need to remember this. In a inscribed triangle, again, we're going to reiterate that if the inscribed triangle, if one side of the inscribed triangle goes through the diameter, that makes the inscribed triangle a right triangle, which makes the chords perpendicular where they touch the circle. It's the only way you can have it. So the diameter, we get a semicircle. We know that that's going to be a right angle, a right triangle, sorry. So that'll help us figure out what the diameters of circles are given side lengths. So we'll be able to do some math that way. From that as well, we're told if it's a quadrilateral, an inscribed polygon has 4 vertices at the quadrilateral, then the opposite angles are supplementary. So remember, they're talking about opposite, but it's like every second angle. So if we look at our picture, I have my sides of my 2 triangles goes through the diameter. So this is the diameter. So that tells me both of these angles are right angles. So when we talk about the quadrilateral with the bigger shape, which I will kind of highlight in my highlighter. So my bigger shape here I know from that that the opposite angles are supplementary. So angle A and angle C are going to add up to 180 degrees. But I look, and they're right triangles, so they have to. It's 90 and a 90 degree angle. They have to add up to 180. That also tells me that angle B and angle D are going to add up to 180 degrees. So again, you'll be able to do work from that with that information to find other measurements and other angle measurements in your circles to solve some problems. Tangents. We talked about this Tuesday, sorry. So the tangent is a point, is one point of tangency. It's a line from some point outside a circle that just touches the circle. I know they're all been drawn like not going through, but we kind of think of when we circumscribe a polygon, that's kind of the sides continue past the circle where they touch. But we always remember it's just barely touching the circle at that point. The tangents are always perpendicular to the radius at that point of tangency. So they're always going to form right angles if you're told something's tangent. So RS is tangent to circle P. So angle PRS is a right angle. And then if there are two external tangents from the same exterior point, like our example here, we have 2 lines drawn from point F, then that tells us that those 2 tangents, when they touch the circle, those 2 tangents are congruent. Does that make sense? So you kind of think of, if we draw in this radius out to point T, and you kind of think back to the shape stuff we worked on, this kind of forms a kite as a polygon. Remember, kites have the 2 consecutive sides are congruent. My radiuses here are congruent. The other sides are congruent. So that kind of tells you that it's a kite shape. Well, then there's information we remember about the diagonals of the kite, but we don't really go into that in the tangent stuff. Okay, so we have our example. We have our point of tangency. AB is tangent to circle C. They want us to find X. So tangent, I know that's a right angle. I'm looking at my right triangle, so now I know I'm probably going to be using the Pythagorean theorem somewhere. Don't get confused. Whenever you see a measurement like outside a tangent like this, don't forget that you have to add the radius in too. This is still part of that side AC, so I have to add that back in. So they're going to have to give you the radius there too. So I know this was 8, if we remember this. So my Pythagorean theorem then is going to be 17 squared. My hypotenuse side is going to equal 8 squared plus x squared. We solve that down. It's 289 equals 64 plus x squared. We move the 64 over. We end up with x squared equals 225. So our x value was 15. So that tells us that x was 15. Again, if we had another point of tangency from point A, we know that side is going to be 15 as well from our rules. I'll draw it in blue if we had it. I know now that here is 15 units as well because a tangent, it has to equal the other tangent from point A. Does everybody remember that? Kind of makes sense? Okay. The circumscribed polygons, the problems you're going to see on the test are figuring out the perimeters of those circumscribed polygons using information we already know. The circles are tangent to all those points, so if I had to draw in my radius, that's going to be a right angle, which will then help you find other information from the stuff we're looking at. Just remember then as well, it's perpendicular to the tangent, so that is really going to cut the points of tangency from point H to, let's call this J. Now I drew one over here, we'll call that K. Remember, these sides have to be congruent because the tangency from the same exterior point. So our example with the problem, we have a circumscribed triangle about circle O. We want to find the perimeter of the triangle. We're given a couple of measurements. We're told AF is 12. So we remember to AD, from A to D, that point of tangency, this side is going to be 12 as well, because tangents from the same exterior point are congruent. Same thing, B to E, B to D have to be the same. So that's going to make BD 6. Same thing, E to C, F to C, going to be the same. Going to be 8. Now you add up all your sides. And I think if I remember correctly, our perimeter for this was 52 units. So those are the types of problems you're going to see in the test with the points of tangency. Okay, and then what we worked on yesterday, the half day, was finding areas. Again, remember, if you're asking for, if they don't tell you they want it rounded, always assume and always just give them the answer in terms of pi. Our example here is find the area of the circle P. They don't tell us to round it, so I'm going to give it in terms of pi. I need to find the radius. My radius for circle P is 6. My formula is pi r squared, so r squared is 36. I can leave it in pi. So my area of that circle is 36 pi meters squared. Don't forget the label meters squared. We're going to be working with circumferences and areas in this test, so you need to be identifying which is which. Okay, and then we talked about, whoops, I miscopied that. I will draw it in blue here because I don't have a picture. We talked about sectors as well. So if I draw in a central angle here, we'll call it central angle is 60 degrees. And now I want the area of my shaded side, which I'll shade in yellow here. I apologize for not having that slide. So we want the area of our shaded circle. Remember that our formula for that is the x over 360 times pi r squared. That's the area of a sector. So we look at what we're looking at. We're trying to find the area of our shaded region, which was the yellow region. My central angle they gave us is 60 degrees. So I know the angle, the central angle for the shaded region is going to be 300. It's just 360 minus 60. So to figure this out, I got 300 over 360 times my diameter, my radius is still 6. So it's going to be times 36 pi. So again, we want exact measurement. We can give exact measurement because they're not asking for us to round it. So I kind of do some math here. I can simplify some stuff down. I end up with, this simplifies really down to 5/6 times 36 pi. So we talk about multiplication. We can do 5/6 times 36 over 1. What this works out to be is just 30 pi is the area of the shaded region, 30 pi meters squared. So I apologize for not having a slide there. I thought I did, but I copied the wrong slide. So remember, area of a sector is the x over 360 times the area formula for a circle. So I hope that helps clear everything up. I hope everybody's kind of ready for this test on Friday. It's not going to be overly difficult because this is a relatively simple unit. The challenge on the test is going to be the algebra parts of the questions that make you have to figure out some answers. There are some problems in the review packet that will do that. So definitely focus on the algebra problems in the review packet. There are a couple of word problems in there as well. Focus on those. And what I will do this afternoon is post the answer key for the review packet out on Google Classroom so that you can check your answers to make sure you're kind of doing the right thing to help you if you have to send me messages and questions like, oh, I got this one wrong, I don't know why. So otherwise, I will see everybody Friday and have a good day, or see everybody Monday because you guys aren't in until Monday. So have a good night and good luck studying.